Welcome, friend, and thank you for being here. Tonight we will move gently through deep time into a world both strange and familiar. Dinosaurs are often imagined as monsters, but they were living animals shaped by patience, adaptation, and change. This is not a story of sudden spectacle, but of quiet endurance across unimaginable ages. Before we begin, if you enjoy these gentle explorations, please consider liking this video and subscribing to the channel. It helps others discover their way here as well. And if a particular science topic ever drifts into your thoughts, you can leave it in the comments. For now, simply settle in and let the journey continue. Dinosaurs were not creatures of constant violence or spectacle, but animals that lived, fed, rested, and endured across ages longer than we can easily imagine. As each fact unfolds, let it arrive without effort. You do not need to hold on to anything. If your thoughts drift, allow them to. This is a quiet journey through ancient Earth, meant to soften curiosity into calm and curiosity into rest. Dinosaurs lived on Earth for more than 160 million years, a span of time so vast it challenges human intuition. They first appeared during the Triassic period, survived the Jurassic, and continued into the late Cretaceous, adapting as continents shifted and climates transformed. During their reign, oceans opened and closed, mountains rose, forests spread, and deserts formed. Entire ecosystems changed shape around them, yet dinosaurs endured. This longevity was not due to strength alone, but flexibility. They evolved into countless forms, filling roles as predators, grazers, scavengers, and flyers. Some grew enormous, others stayed small. Some thrived in heat, others near the poles. When we compare this to humanity's brief presence, the contrast is striking. Dinosaurs were not a failed experiment. They were among the most successful groups of animals ever to walk on land, quietly dominating Earth for longer than any mammal ever has in recorded evolutionary history alone. Time on this scale reshapes how we see dinosaurs. They were not rushing toward extinction, but settled into the rhythms of Earth itself. To understand them, we begin not with drama, but with patience, and with the moment they first appeared long before mammals, birds, or humans existed here today. Dinosaurs are often imagined as oversized versions of modern lizards, but this image is misleading. Early scientists worked with limited fossil evidence and naturally compared unfamiliar bones to animals they already knew. Lizards crawl with limbs splayed outward, their bodies close to the ground. Dinosaurs, by contrast, stood tall. Their legs were positioned directly beneath their bodies, supporting weight in a way more similar to birds and mammals. This upright stance allowed efficient movement, greater endurance, and, in some species, remarkable speed. Dinosaurs also differed internally. Their hip structures, growth patterns, and even bone tissue were distinct from lizards. Many dinosaurs grew rapidly, especially in their early years, suggesting more active lifestyles than modern reptiles. Calling dinosaurs giant lizards hides their uniqueness and flattens a vast diversity into a single incorrect image. They were not scaled-up reptiles we recognize today, but something entirely their own, shaped by evolutionary paths that no longer exist in quite the same form. Understanding this difference helps clear away old misconceptions. Dinosaurs were not exaggerations of modern animals. They were a separate experiment in life, one that followed its own rules. From here, it becomes easier to see how scientists began to recognize dinosaurs as something far more unusual than anyone first imagined. Dinosaurs belong to a scientific group known as Dinosauria, defined not by size or ferocity, but by anatomy. Membership in this group depends on specific skeletal features, especially in the hips, legs, and pelvis. These shared traits indicate common ancestry rather than appearance. Dinosauria includes an enormous range of species, from towering sauropods to small feathered hunters. What unites them is a particular arrangement of bones that allowed upright posture and efficient movement. This definition matters because it separates dinosaurs from other ancient reptiles that lived alongside them, such as marine reptiles and flying pterosaurs, which were not dinosaurs at all. Dinosauria emerged during the Triassic period when Earth was recovering from a mass extinction. In that unstable world, this new group quietly diversified, experimenting with body plans that would later dominate the planet for millions of years. Once dinosaurs are defined by structure instead of myth, their story becomes clearer. They were not just big animals, but members of a lineage with shared origins. That lineage would soon spread across the globe, adapting to nearly every environment Earth could offer. The earliest dinosaurs appeared during the Triassic period, over 230 million years ago. At that time, Earth looked very different. All major continents were fused into a single landmass called Pangaea, and life was recovering from the largest mass extinction in history. Early dinosaurs were not dominant. They were small, lightly built, and lived alongside many competing reptiles. What set them apart was efficiency. Their upright posture required less energy to move, and their bodies handled heat more effectively. Over time, these advantages mattered. As climates fluctuated and competitors faded, dinosaurs slowly expanded into new ecological roles. This rise was gradual, not sudden. For tens of millions of years, dinosaurs remained one group among many. Their eventual dominance was the result of persistence rather than immediate superiority. This slow beginning reminds us that success in evolution often starts quietly. Dinosaurs did not burst onto the scene as rulers. They waited, adapted, and endured. With time on their side, they would reshape life on land in ways no one could have predicted. Dinosaur fossils have been found on every continent, even Antarctica. During the age of dinosaurs, the continents were arranged differently, and Antarctica was not the frozen desert we know today. It supported forests, rivers, and diverse animal life. Dinosaurs walked beneath long summer sunlight and survived extended winter darkness. Fossils from polar regions show species adapted to cooler temperatures and seasonal extremes. This global distribution demonstrates remarkable adaptability. Dinosaurs thrived in tropical swamps, arid deserts, coastal plains, and polar forests. As tectonic plates slowly shifted continents apart, dinosaur populations became isolated, leading to new species evolving independently. Their worldwide presence explains their incredible diversity. Few groups of land animals have ever achieved such broad geographic success. This global spread shows dinosaurs were not fragile specialists. They were resilient travelers of deep time. Understanding where they lived helps explain how they endured environmental change again and again, long before humans ever appeared on the planet. Dinosaurs are often remembered for their giants, but size variation was one of their greatest strengths. Some dinosaurs weighed more than 70 tons, while others were no heavier than a modern pigeon. Tiny species darted through undergrowth, climbed trees, or hunted insects. Large species reshaped landscapes by feeding on vast quantities of vegetation. This range allowed dinosaurs to fill nearly every ecological niche on land. Small dinosaurs could reproduce quickly and adapt rapidly. Large dinosaurs deterred predators simply through size. Together, this spectrum created stable, complex ecosystems. Size did not define success. Survival depended on fitting into an environment effectively. Dinosaurs explored every option evolution offered, from miniature precision to overwhelming scale. Remembering this diversity softens the image of dinosaurs as only giants. They were communities, not caricatures. As we move forward, the familiar giants remain important, but so do the quiet, small-bodied species that shared their world unnoticed. Birds are not merely related to dinosaurs, they are dinosaurs. Modern birds descended directly from small feathered theropod dinosaurs. This connection is supported by overwhelming evidence: feathers, wishbones, hollow bones, similar lung systems, and even nesting behavior. When non-avian dinosaurs went extinct, this one branch survived. Over time, these survivors diversified into the thousands of bird species we see today. Sparrows, eagles, penguins, and owls all carry the legacy of the dinosaur age within their bones. This realization reshapes extinction itself. Dinosaurs did not completely vanish, they transformed. The world never truly left the age of dinosaurs behind, it simply changed how they appear. This living connection brings deep time into the present. When you hear birdsong or watch wings lift into the air, you are witnessing the continuation of an ancient story. Dinosaurs still walk among us, lightly now, carried on feathers instead of thunderous steps. Dinosaurs belonged to a broader group called reptiles, but not in the everyday sense. Under a modern biological classification, birds are also reptiles. Dinosaurs, birds, and crocodilians all belong to a group called archosaurs. Lizards and turtles fall on different branches of the reptile family tree. This means dinosaurs were more closely related to birds and crocodiles than to snakes or lizards. Saying dinosaurs were closer to birds than reptiles is misleading because birds are reptiles. What changed over time was not category, but form. Feathers, flight, and small body size emerged within one dinosaur lineage. Understanding this clears confusion created by older classification systems and brings dinosaur biology into clearer focus. This clarity helps replace outdated language with precision. Dinosaurs were not separate from reptiles. They were part of a living lineage still present today. From this foundation, their anatomy and behavior begin to make much more sense. One defining feature of dinosaurs was their upright posture. Their legs extended straight beneath their bodies, unlike the sprawling stance of most reptiles. This structure supported greater body weight and allowed more efficient movement over long distances. Upright posture reduced energy use, improved breathing while moving, and helped regulate body temperature. It also freed the forelimbs for other uses, such as grasping, display, or flight in later species. This posture is one reason dinosaurs could grow so large without collapsing under their own weight. It also contributed to their endurance and dominance across diverse environments. Upright walking was not just a physical trait, it was a strategic advantage shaped by evolution. This simple shift in posture changed everything. How dinosaurs moved influenced how they ate, hunted, and survived. From here, we can begin to understand why dinosaurs were so successful across deep time and so difficult to replace. For over 150 million years, dinosaurs were the primary large animals on land. They shaped ecosystems as predators, herbivores, and scavengers. Plant life evolved in response to their feeding habits, while smaller animals adapted to live alongside or beneath them. Dinosaurs influenced soil, vegetation patterns, and even the movement of nutrients across landscapes. Their long dominance was not static. Species rose and fell, climates shifted, and continents moved. Yet dinosaurs remained central to life on land. This stability across change is rare in evolutionary history. Dinosaurs were not temporary rulers. They were long-term architects of Earth's surface ecosystems. This long reign sets the stage for everything that follows. Understanding how dinosaurs shaped the world prepares us to explore how they lived day to day. With that foundation, we can begin looking more closely at their bodies, behaviors, and hidden complexities next. Some of the largest dinosaurs reached weights exceeding 70 tons, making them the heaviest land animals ever to exist. Sauropods such as Argentinosaurus and Patagoteton carried bodies heavier than a fully loaded commercial airplane. Their bones were immense, yet carefully engineered, filled with air pockets that reduced weight without sacrificing strength. Muscles, tendons, and ligaments work together to support bodies that pushed the limits of biology. These animals fed constantly, consuming enormous amounts of vegetation to fuel their bulk. Their size offered protection from predators, but it also required balance, efficiency, and slow, deliberate movement. Despite their mass, these giants were not clumsy. Trackways show steady, purposeful walking, suggesting bodies finely tuned to their environment rather than overwhelmed by their own scale. Size at this level was not accidental. It was the result of millions of years of gradual refinement. From these giants, we can begin to explore how length, height, and proportion reshaped dinosaur bodies in remarkable ways. Length, not just weight, defined the largest dinosaurs. Certain sauropods stretched over 100 feet from head to tail, longer than 3 school buses parked end to end. Much of this length came from their necks and tails, which extended far beyond the core of the body. These elongated forms allowed dinosaurs to feed across wide areas without moving much, conserving energy. Their tails acted as counterbalances, stabilizing their long necks and massive torsos. Fossil skeletons reveal that these animals were not stretched thin, but built with repeating vertebrae that distributed stress evenly. Their bodies were not exaggerated accidents, but carefully structured systems scaled upward. Length transformed how these dinosaurs interacted with their world. They could reach food others could not, and dominate space simply by existing within it. From here, it becomes possible to ask which dinosaurs pushed size to its absolute limit. Among all known dinosaurs, Argentinosaurus stands as a leading candidate for the largest land animal to ever walk the Earth. Fragmentary fossils suggest a creature over 100 feet long and weighing more than 70 tons. Even its individual bones are staggering. A single vertebra outweighs most adult humans. Argentinosaurus lived in what is now South America, sharing its world with massive predators that hunted in groups. To survive, it likely relied on sheer size, herding behavior, and constant movement through vast landscapes. Its skeleton reveals strength paired with lightness, using air-filled bones to support extreme mass. Argentinosaurus represents the upper boundary of what life on land could achieve. Thinking about Argentinosaurus stretches the imagination. It reminds us that evolution sometimes pushes against physical limits. Yet even such giants began small, which leads naturally to the opposite extreme of dinosaur size. Not all dinosaurs were giants. Some species were astonishingly small. The smallest known dinosaurs weighed less than a modern pigeon and could fit comfortably in the palm of a human hand. These tiny dinosaurs were agile, lightweight, and often feathered. Their small size allowed them to move through dense vegetation, climb, glide, or dart away from danger quickly. They likely fed on insects, seeds, and small animals, occupying niches similar to modern birds. Fossils of these species are rare because delicate bones preserve poorly, but discoveries continue to reveal how important small dinosaurs were to ancient ecosystems. These miniature dinosaurs remind us that success did not require size. Survival often favored speed, flexibility, and stealth. With that in mind, we can now look at how size varied even among familiar dinosaur groups. Several dinosaur species were no larger than modern chickens. These small theropods lived quick, alert lives, constantly aware of predators larger than themselves. Feathers provided insulation and may have aided in display or balance. Their lightweight frames allowed rapid movement and sudden changes in direction. Some hunted insects or small vertebrates, while others scavenged. Being small also meant faster reproduction and shorter lifespans, strategies that helped populations survive instability. These dinosaurs were not failures or juveniles of larger species. They were fully developed adults adapted to their environments. Remembering these chicken-sized dinosaurs helps soften the stereotype of dinosaurs as slow giants. Their world was alive with motion at every scale. From here, we can return to the giants, focusing on one of their most defining features. The necks of some sauropod dinosaurs stretched more than 30 feet long, longer than many entire animals. These necks were composed of numerous vertebrae, each carefully shaped to reduce weight while maintaining strength. Air-filled cavities lightened the bones, while strong muscles and ligaments supported movement. Such necks allowed sauropods to feed at different heights and across wide areas without moving their massive bodies. They could browse treetops or sweep low vegetation with slow, controlled motions. Despite their length, these necks were not limp. Fossil evidence shows they were held in specific ranges of motion suited to feeding strategies. These enormous necks were tools, not ornaments. They reshaped landscapes simply by reaching into them. But lifting such a structure required more than bone and muscle. It demanded extraordinary internal systems. To support bodies of such immense size, sauropods required powerful cardiovascular systems. Pumping blood from the heart to a brain positioned high above the ground was no simple task. Scientists believe their hearts were large and strong, capable of maintaining steady circulation despite gravity. Their blood vessels were likely reinforced, and their posture helped reduce strain. Efficient oxygen delivery supported slow but continuous movement. Without such systems, sauropods could not have fed, grown, or survived. Their internal biology matched their external scale, revealing animals finely adapted to their own enormity. These unseen systems remind us that size is supported by invisible work within the body. Once circulation is considered, we can look outward again to features that balanced these massive forms. Sauropod tails were not simply extensions of the spine, they were essential balancing tools. Stretching behind the body, these long, muscular tails countered the weight of the neck and torso. This balance allowed stable walking and efficient movement. In some species, the tail narrowed into a flexible whip-like structure capable of rapid motion. In others, it acted as a steadying beam. Vertebrae near the tail tip were lightweight and numerous, supporting both flexibility and strength. The tail helped distribute mass evenly, preventing dangerous strain on the hips and legs. Balance was key to survival at massive scales. With neck and tail working together, sauropods achieved stability. That stability allowed dinosaurs to explore extremes of size, unlike anything before or since. Dinosaurs hold records for both the tallest and heaviest land animals ever known. Brachiosaurus reached heights comparable to multi-story buildings, while sauropods like Argentinosaurus claimed unmatched mass. These extremes did not exist in isolation. They were part of ecosystems that supported a wide range of body plans. Evolution explored vertical space with long necks and horizontal space with length and bulk. These giants reshaped plant communities and influenced climate through their feeding and movement. No mammal has ever matched their size on land. These records emphasize how unique the dinosaur era was. Earth once supported forms of life far beyond modern limits. Yet size alone did not guarantee longevity, leading to an important realization. Despite their enormous size, not all large dinosaurs survived environmental change. Smaller dinosaurs often proved more adaptable, reproducing faster and adjusting diets more easily. Fossil records show both large and small species rising and falling over time. Survival favored flexibility rather than dominance. Even the largest dinosaurs depended on stable ecosystems and abundant food. When conditions shifted, size became a liability. This truth challenges the idea that power ensures permanence. In evolution, balance matters more than force. Understanding this prepares us to explore how dinosaurs adapted in other ways beyond size. From skin and feathers to color and insulation, their bodies reveal quieter strategies for survival that were just as important as strength. For much of the 20th century, dinosaurs were imagined as scaly reptiles, but fossil discoveries have steadily changed that picture. Many dinosaurs, especially smaller theropods, were covered in feathers. Some feathers were simple, hair-like filaments that provided insulation. Others were complex, with branching structures similar to those seen in modern birds. These feathers evolved long before flight and served multiple purposes, including warmth, display, and communication. Feathered fossils from China preserve extraordinary detail, showing layers of plumage wrapped around arms, tails, and bodies. This evidence demonstrates that feathers were not rare or unusual, but widespread among certain dinosaur groups. The presence of feathers suggests active metabolisms and dynamic behaviors, painting a picture of dinosaurs as warm, alert animals rather than sluggish creatures. Feathers quietly redefine how we imagine dinosaurs. They soften silhouettes and blur the line between ancient reptiles and modern birds. From here, it becomes important to understand why feathers appeared in the first place. Feathers did not originate as tools for flying. Long before any dinosaur left the ground, feathers served other functions. Early feathers likely helped regulate body temperature, trapping air close to the skin. They may also have played roles in visual display, making individuals more noticeable to mates or rivals. Over time, some feathers became larger and more structured, capable of catching air. Only later did certain dinosaurs begin using feathered limbs to glide, and eventually to fly. This gradual progression shows how evolution repurposes existing traits rather than inventing new ones from nothing. Flight was an outcome, not the original goal. This slow transformation reminds us that complex abilities often emerge step by step. Feathers were first about survival and signaling, not escape into the sky. That versatility allowed them to take on new roles as dinosaurs continued to adapt. Many small and juvenile dinosaurs were covered in soft, down-like feathers. These fine filaments functioned much like the down on modern birds, providing insulation and helping maintain body temperature. This suggests that at least some dinosaurs were warm-blooded or had elevated metabolisms requiring thermal regulation. Downy coverings would have been especially important for hatchlings and small species vulnerable to heat loss. Fossils preserve these filaments as fuzzy outlines surrounding bones, offering rare glimpses into texture rather than just shape. Insulation allowed dinosaurs to remain active in cooler climates and during temperature swings. Downy feathers hint at tenderness in a world often imagined as harsh. They suggest care, vulnerability, and warmth. From insulation, feathers also became tools of expression, shaping how dinosaurs appeared to one another. Not all feathers were subtle. Some dinosaurs carried long, elaborate feathers on their arms, tails, or heads. These structures may have been brightly coloured or patterned, designed to attract mates or signal dominance. Display feathers could make individuals appear larger or more impressive without adding significant weight. In social species, visual communication mattered. Feathers became flags of identity, health, and status. Fossil evidence shows asymmetrical feathers and elongated plumes unlikely to be useful for flight, reinforcing their role in display rather than movement. These ornamental features reveal dinosaurs as social animals with visual languages. Their world was not only about survival, but also about signaling and interaction, setting the stage for an even richer palette of appearance. Dinosaurs did not all share the same outer covering. Some species had traditional reptile-like scales, others bore feathers, and some combined both. Certain dinosaurs even had quill-like structures projecting from their skin. These coverings varied by species, body region, and life stage. This diversity suggests adaptation to specific environments and behaviors. Armor-like scales protected some animals, while feathers provided insulation or display. The surface of a dinosaur was not uniform or dull, but textured and complex. Recognizing this variety replaces a single outdated image with many living forms. Dinosaurs wore their adaptations on the outside. To complete that picture, scientists began asking not just how dinosaurs felt to the touch, but how they looked in color. For a long time, dinosaur color was considered unknowable. That changed with the discovery of microscopic pigment structures preserved in fossil feathers. These structures, called melanosomes, allow scientists to infer color based on their shape and arrangement. Evidence suggests some dinosaurs were black, brown, red, and even patterned. Color likely served functions such as camouflage, mating display, and species recognition. Bright colors may have flashed during movement or social interactions, turning dinosaurs into living signals within their environments. Color brings immediacy to ancient life. It transforms fossils into animals with presence and personality. Beyond simple hues, some dinosaurs may have displayed even more striking visual effects. Under powerful microscopes, fossilized feathers sometimes reveal melanosomes, the same structures that give color to modern bird feathers. Rod-shaped melanosomes often indicate black or gray colors, while spherical ones suggest reddish or brown tones. By comparing fossil melanosomes to those in living birds, scientists can reconstruct color patterns with surprising accuracy. This technique has revealed banding, shading, and contrast in dinosaurs once thought colorless. These discoveries rely on careful analysis, showing how small details can survive vast spans of time. Microscopic evidence adds depth to the fossil record. It shows that even delicate features can leave lasting traces. Some of these traces hint at colors beyond matte shades, reaching into shimmering effects. Certain fossil melanosomes suggest iridescence, a shimmering quality seen in modern hummingbirds and starlings. Iridescent feathers change color depending on light angle, creating flashes of green, purple, or blue. This effect is often used in display and communication. Small feathered dinosaurs with iridescent plumage would have caught sunlight as they moved, producing subtle visual signals. Such coloration implies complex social behavior and refined sensory perception. The prehistoric world was likely filled with shifting color and light. Iridescence adds elegance to our view of dinosaurs. It suggests a world alive with motion and shimmer. From here, color also played quieter roles, helping dinosaurs blend into their surroundings. Not all dinosaur colors were bold. Many species likely used muted tones and patterns for camouflage. Stripes, spots, and gradients could break up body outlines, making animals harder to see among foliage and shadow. Smaller dinosaurs especially benefited from blending in. At the same time, some species balanced camouflage with display, revealing brighter colors only during certain behaviors. Color became a flexible tool, shifting between concealment and communication depending on context. This dual use of color reflects balance. Dinosaurs navigated worlds of danger and opportunity, using appearance to hide or to be seen. That balance contributes to a broader understanding of how vivid their environments truly were. Taken together, feathers, textures, and colors reveal that the dinosaur world was far from dull. Forests and plains were filled with movement, pattern, and visual complexity. Dinosaurs interacted with one another through shape, color, and display, just as animals do today. The ancient landscape was alive with contrast and detail. Seeing dinosaurs this way replaces grey silhouettes with living presence. This richness prepares us to move beyond appearance. With bodies covered, coloured, and expressive, dinosaurs also moved in remarkable ways. From walking to running to swimming, their abilities shaped how they lived across ancient Earth. Not all dinosaurs were slow or lumbering. Some were built for speed. Lightweight theropods with long legs, narrow hips, and stiffened tails were capable of rapid bursts of movement. Fossil limb proportions and muscle attachment sites suggest that certain species could reach speeds exceeding those of the fastest human runners. Speed was a powerful survival tool. Fast dinosaurs could chase prey, escape predators, or quickly reposition within their environments. Their tails acted as dynamic counterbalances, allowing sharp turns without losing stability. These animals were not built for endurance marathons, but for sudden acceleration and agile motion. In open plains or forest clearings, speed could mean the difference between life and death. This ability reminds us that dinosaurs explored many solutions to survival. While some relied on size, others trusted agility. From speed on land, we can turn to the internal structures that made such movement possible. Many dinosaurs possess skeletons that were both strong and surprisingly light. Bones were often hollow or honeycombed, reinforced by internal struts. This design reduced weight without sacrificing strength. Lighter skeletons required less energy to move, supporting speed and endurance. In large dinosaurs, this adaptation prevented collapse under extreme mass. In smaller species, it enhanced agility. These skeletal structures also supported complex breathing systems that further improved oxygen delivery during movement. Dinosaur bones were not simple supports. They were engineered systems optimized for motion. This internal efficiency helps explain how dinosaurs could grow large or move quickly without exhaustion. Structure supported function. From bones, we can now look at how dinosaurs interacted with environments beyond dry land. Evidence from fossilized trackways shows that some dinosaurs were capable swimmers. Footprints preserved in ancient riverbeds reveal claw marks scraping the bottom while bodies floated above, buoyed by air-filled lungs. Both small and large dinosaurs appear in these records. Swimming would have allowed dinosaurs to cross rivers, escape predators, or access new feeding areas. They did not need specialized fins or tails to paddle effectively. Simple body motion and strong limbs were enough. Water was not a barrier, but another space to navigate. This ability expanded the reach of dinosaurs across landscapes. It allowed movement through environments that might otherwise divide populations. From swimming, we can consider even more unusual ways dinosaurs moved through their world. Certain small feathered dinosaurs show anatomical features consistent with gliding. Elongated limbs, feathered arms and legs, and wide surface areas suggest they could catch air while leaping from elevated positions. These dinosaurs likely moved between trees or from canopy to ground, reducing the risk of falls. Gliding required control rather than power, relying on balance and feather arrangement. This behavior represents an early exploration of aerial movement, distinct from true flight, but closely related to it. Gliding shows how dinosaurs experimented with space above the ground. They did not remain confined to the forest floor. From gliding, the path toward powered flight becomes easier to imagine. Many fast-running dinosaurs relied on long, stiffened tails to maintain balance. As they ran, the tail countered forward motion, preventing tipping. This allowed rapid acceleration and sudden turns. The tail acted as a dynamic stabilizer, shifting position as the body moved. Fossilized vertebrae show stiffening rods that limited tail flexibility in some species, optimizing it for balance rather than display. This design allowed dinosaurs to move efficiently even at high speeds. Balance is often invisible but essential. With tails and limbs working together, dinosaurs could navigate complex terrain. That coordination extended beyond individuals into group movement. Fossil evidence suggests that certain dinosaurs traveled long distances in response to seasonal changes. Trackways and chemical signatures in bones indicate movement between feeding grounds as climates shifted. Migration allowed access to fresh vegetation and safer breeding areas. Large herbivores likely moved in herds, following predictable routes. Migration required memory, coordination, and endurance. It tied dinosaurs to rhythms of Earth itself. These seasonal journeys reveal planning and persistence. Dinosaurs were not confined to small territories. Their lives unfolded across landscapes that changed with time. Fossilized footprints provide direct records of dinosaur activity. Unlike bones, which show anatomy, footprints capture moments. Some tracks reveal walking side by side. Others show running strides or sudden changes in direction. In rare cases, impressions of resting bodies and tails are preserved. These traces freeze movement in stone, offering glimpses into daily life. Footprints show pace, posture, and even hesitation. Such evidence brings dinosaurs closer to us. We see not just what they were, but what they did. From these frozen steps, patterns of social life begin to emerge. Many fossil trackways consist of multiple footprints moving together in the same direction. These patterns suggest herd behavior. Group movement provided protection, especially for juveniles. Adults may have surrounded young or coordinated travel. Trackways also show variation in size, indicating mixed age groups. This social structure mirrors behaviors seen in modern large animals. Herding adds another layer to dinosaur life. It suggests cooperation rather than constant conflict. From social movement, we can explore how dinosaurs rested, interacted, and shared space. In rare cases, trackways preserve impressions of dinosaurs stopping to rest. These fossils include marks from folded limbs, tails touching the ground, and bodies lowering into mud. Such evidence suggests dinosaurs paused during travel, perhaps to conserve energy or remain alert to danger. Resting behavior indicates control over posture and comfort. It shows dinosaurs were not always in motion. Rest adds gentleness to their story. Even giants needed stillness. From resting bodies, we can now consider how dinosaurs interacted playfully or unpredictably with their environment. Some fossilized footprints show signs of slipping, skidding, or sliding through wet sediment. Claw marks scrape forward, while footprints stretch or distort. These traces suggest dinosaurs occasionally lost footing or moved deliberately through mud or shallow water. Such moments reveal imperfection and adaptation. Dinosaurs navigated uneven ground just as animals do today. These imperfect traces humanize dinosaurs. They show lives lived in motion, mistake, and adjustment. With movement understood, we can turn next to how dinosaurs fed, hunted, and shaped the ancient food web. Many dinosaurs survived entirely on plants, shaping ecosystems through constant feeding. Herbivorous dinosaurs consumed leaves, ferns, cycads, conifers, and later flowering plants. Their diets required specialized bodies built for processing enormous amounts of vegetation. Large guts allowed slow fermentation, extracting nutrients from tough plant fibers. Some species grazed low to the ground, while others fed high in trees, dividing resources and reducing competition. Herbivores were not passive creatures. Their feeding habits influenced plant evolution, encouraging rapid regrowth, defensive structures, and seasonal cycles. Over millions of years, plants and dinosaurs shaped one another in quiet partnership, each responding to the other's presence across changing landscapes. This plant-based way of life anchored dinosaur ecosystems. From these steady grazers arose complex food webs, setting the stage for predators, scavengers, and the balance that followed. Alongside herbivores lived powerful carnivorous dinosaurs that occupied the top of the food chain. These apex predators hunted, scavenged, and controlled population balance within ecosystems. Species such as Tyrannosaurus rex and Allosaurus possessed keen senses, strong legs, and specialized teeth for tearing flesh. Their presence influenced how prey animals moved, grouped, and evolved defenses. Apex predators were not constant killers. They expended energy carefully, choosing opportunities rather than chasing endlessly. Their role was ecological, shaping behavior and maintaining balance rather than simply dominating through force. Predators completed the circle of life in dinosaur worlds. With hunters and hunted established, we can now examine the tools that made feeding possible, beginning with one of evolution's most impressive inventions. Certain plant-eating dinosaurs, particularly hadrosaurs, possessed extraordinary dental systems. Their mouths contained hundreds of tightly packed teeth arranged in rows called dental batteries. As teeth wore down from grinding tough vegetation, new ones continuously moved into place. At any given time, a hadrosaur might have had over 1,000 teeth at various stages of growth. This system allowed efficient chewing, uncommon among reptiles. Their jaws functioned like natural food processors, breaking down fibrous plants with precision that rivaled modern mammals. These remarkable mouths reveal how feeding drove innovation. Teeth were not static tools but renewable resources, constantly refreshed. From here, we can explore how other dinosaurs maintained their teeth through equally impressive strategies. Unlike humans, many dinosaurs replaced their teeth continuously. As teeth chipped, broke, or wore down, new ones formed beneath them, pushing upward. This was especially important for predators that bit bone and herbivores that ground abrasive plant matter. Fossil jaws often show multiple generations of teeth stacked together, waiting their turn. This constant renewal ensured dinosaurs never faced starvation due to dental failure. Teeth were treated as expendable tools, not permanent fixtures. This replacement strategy allowed dinosaurs to eat without hesitation. It supported long lives and demanding diets. With teeth accounted for, attention turns to how dinosaurs processed food beyond the mouth. Many herbivorous dinosaurs evolved jaws capable of complex motion. Instead of simple up and down bites, some species chewed side to side, increasing efficiency. Muscles and joint structures allowed precise grinding, reducing plant matter before swallowing. This adaptation extracted more nutrients and reduced digestion time. Advanced chewing supported larger body sizes and higher energy demands. It also allowed dinosaurs to exploit tough, fibrous plants that other animals could not digest effectively. Efficient chewing made herbivory viable at massive scales, but chewing alone was not always enough. Some dinosaurs relied on additional tools hidden within their bodies. Certain dinosaurs swallowed smooth stones called gastroliths to help grind food inside their stomachs. These stones acted like internal millstones, breaking down tough plant fibers during digestion. Gastroliths have been found clustered within rib cages, polished from repeated use. This behavior is still seen in modern birds and reptiles. Swallowing stones allowed dinosaurs without complex teeth to process food effectively, turning simple materials into powerful digestive tools. This internal strategy shows how evolution uses simple solutions. When teeth were insufficient, stones filled the gap. From digestion, we can now examine direct evidence of what dinosaurs ate. On rare occasions, fossils preserve the remains of a dinosaur's last meal. These discoveries include partially digested plants, fish, small animals, and even other dinosaurs. Such finds confirm dietary theories built from anatomy alone. One fossilized microraptor was found with bird bones in its stomach, revealing predatory behavior. These snapshots capture moments of daily survival, frozen across millions of years. These preserved meals bring intimacy to ancient life. They show dinosaurs not as abstractions, but as animals making ordinary choices. From meals, attention naturally shifts to what happened after digestion. Fossilized dinosaur dung, known as coprolite, is one of the most informative fossil scientists study. Though unglamorous, coprolites preserve seeds, bone fragments, shells, and plant fibers. They reveal diet, digestion, and ecosystem structure. By analyzing coprolites, researchers learn which plants grew in certain regions and how food chains were organized. Even waste became a record of life, quietly preserving information long after bones turned to stone. Coprolites remind us that no detail is too small to matter. Even discarded material carries stories. Some of those stories are remarkable in scale. Among the largest coprolites ever discovered are specimens weighing over 40 pounds, likely produced by massive carnivorous dinosaurs. These enormous fossils contain crushed bone fragments, confirming diets that included entire animals. The size of these coprolites reflects both the scale of their producers and the intensity of their feeding. Such finds help scientists estimate metabolism, digestion speed, and feeding frequency in large predators. These immense remnants highlight the physical reality of dinosaur life. Eating, digestion, and waste were all scaled up. From digestion, we return to the broader role dinosaurs played in shaping plant life. Dinosaurs played an important role in plant dispersal. Seeds swallowed during feeding passed through digestive systems and were deposited far from the parent plant. This process helped spread vegetation across vast areas. Coprolites containing intact seeds provide direct evidence of this partnership. Large herbivores acted as moving gardens, reshaping plant distribution simply by living their lives. This quiet cooperation shaped ancient landscapes. Plants fed dinosaurs, and dinosaurs carried plants forward. With feeding understood, we can now explore how dinosaurs defended themselves in a world shaped by constant interaction. Certain dinosaurs evolved thick protective armor made of bone embedded directly into their skin. These bony plates, called osteoderms, formed natural shields across their backs, sides, and sometimes tails. Armored dinosaurs such as ankylosaurs carried this protection like living fortresses. The armor varied in size and shape, from small nodules to large overlapping plates, creating a flexible yet resilient defense. This protection reduced vulnerability to predators and allowed slow-moving herbivores to survive in dangerous environments. Armor was costly to grow and maintain, but it provided long-term security in ecosystems where large predators were common. This defensive strategy shows that dinosaurs did not rely solely on speed or size. Some chose endurance and protection instead. From armor, we move to one of the most dramatic defensive weapons ever evolved. Ankylosaurs carried one of the most formidable weapons in the dinosaur world, a heavy tail club made of fused bone. This structure evolved at the end of the tail, supported by reinforced vertebrae and powerful muscles. When swung, the club could deliver crushing blows capable of breaking bone. Fossil evidence suggests these weapons were used defensively against predators, aiming for legs to disable attackers. The tail club turned a slow-moving herbivore into a dangerous opponent. Predators approaching from behind risked serious injury. The tail club transformed defense into offense. Ankylosaurs were not just protected, but armed. From blunt force, we can explore a different kind of defensive weapon, sharp and precise. Stegosaurus carried long, pointed spikes at the end of its tail, forming a weapon known as the thagomizer. These spikes were solid, sharp, and well-positioned for swinging strikes. Fossilized bones of predators show puncture wounds matching Stegosaurus spikes, indicating real combat. The tail was flexible and muscular, allowing wide arcs of motion. Despite having a relatively small brain, Stegosaurus possessed effective defenses that compensated for limited intelligence. The tail spikes provided a simple, reliable way to deter attacks. These spikes remind us that defense does not require complexity. Sometimes a direct solution is enough. From tails, we turn toward another iconic form of dinosaur weaponry. Horned dinosaurs such as Triceratops developed prominent horns extending from their faces. The largest horns reached over 3 feet in length and were made of solid bone covered in keratin. These horns likely served multiple purposes, including defense against predators and contests with rivals. Fossil skulls show signs of wear, fractures, and healing, evidence that horns were actively used. Combined with large bony frills, horns made ceratopsians imposing figures in their environments. Horns added both protection and display. They communicated strength visually before physical contact was needed. From horns, we can explore how dinosaurs healed after injury. Fossilized horns and frills often contain healed fractures and regrown bone. This indicates that dinosaurs survived injuries that would have been fatal to less resilient animals. Healing suggests strong immune responses and long lifespans. Injuries may have resulted from combat, accidents, or predator attacks. The ability to recover allowed dinosaurs to continue breeding and contributing to populations. Healing also suggests that many injuries occurred within species interactions rather than constant predation. These scars tell stories of survival. Dinosaurs lived dangerous lives, but often endured. From healing horns, we can examine the possibility of regeneration itself. Evidence from bone structure suggests that certain dinosaurs could partially regrow damaged horn tissue. While not full regeneration like some modern reptiles, this repair restored functionality over time. Regrowth would have been essential for species relying on horns for defense or mating displays. This ability added resilience to physical confrontation, allowing repeated use of the same structures throughout life. Regrowth reflects evolutionary investment in defense. Horns were important enough to repair. From horns, attention turns to an even more unusual adaptation involving the skull itself. Pachycephalosaurs possessed thick, rounded skull domes composed of dense bone. These domes could exceed 10 inches in thickness, creating helmet-like structures. Scientists believe these skulls evolved to withstand impact. The surrounding neck muscles and vertebrae supported the head during forceful collisions. The dome transformed the head into a tool rather than a vulnerability. This unusual anatomy suggests behaviors beyond simple feeding or defense. It points towards social interaction, competition, and ritualized conflict. Fossil evidence shows healed damage and stress patterns in pachycephalosaur skulls, supporting the idea that they head-butted one another. Much like modern rams, these dinosaurs may have charged and collided during contests for dominance or mates. Such behavior would have required precise alignment and strong neck support. Headbutting may have been ritualized, limiting injury while resolving social hierarchy. These contests reveal that dinosaurs engaged in complex social behaviors. Combat was not always about survival, but about communication. From blunt force, we move to one of the most precise weapons in the dinosaur arsenal. Raptor dinosaurs carried large, curved claws on each hind foot. These claws were held off the ground to remain sharp. In hunting, the raptor could leap and drive the claw into prey, gripping and slashing with precision. The claw was not used for running, but for combat. Its shape and wear patterns show repeated use. Combined with speed and coordination, this weapon made even small raptors deadly predators. The sickle claw demonstrates how precision can rival size. With this weapon, agility became lethal. From claws, we can examine how dinosaurs maintained their sharpness. Raptor claws were maintained by posture and behavior. By holding the claw raised while walking, it avoided wear from the ground. Keratin covering the claw allowed it to sharpen naturally through use. Fossil evidence shows minimal abrasion at the tip, indicating deliberate preservation. This ensured readiness during sudden attacks. Sharpness required discipline. Raptors treated their claws as vital tools. With defense and weaponry explored, we can now shift toward how dinosaurs sensed, communicated, and perceived their world. Many dinosaurs relied heavily on sight to survive. Fossil skulls show large eye sockets, suggesting well-developed vision in numerous species. Predatory dinosaurs in particular had forward-facing eyes, allowing binocular vision and depth perception useful for judging distance when hunting. Herbivores often had eyes positioned more to the sides, giving them wide fields of view to detect predators. The structure of the eye sockets and surrounding bones indicates that dinosaurs could see movement clearly and react quickly. Vision was essential in open plains, forests, and low-light conditions. Sharp eyesight helped dinosaurs navigate terrain, locate food, recognize companions, and sense danger long before it arrived. Good vision shaped how dinosaurs interacted with their world. It influenced posture, movement, and behavior. From sight, we can turn to another sense that carried information across long distances. Hearing played an important role in dinosaur survival. Fossilized skulls preserve inner ear structures that reveal sensitivity to sound. Some dinosaurs could detect low-frequency vibrations, while others likely heard higher-pitched noises. Keen hearing would have helped locate prey, detect predators, and communicate within groups. Sound travels farther than sight in dense forests or darkness, making hearing especially valuable. Dinosaurs may have relied on subtle cues like footsteps, calls, or ground vibrations to understand their surroundings. Listening expanded awareness beyond what eyes could see. With hearing and vision combined, dinosaurs experienced a rich sensory world. That world also included sounds humans may never have been able to hear. Certain dinosaurs, particularly large herd animals, may have been sensitive to infrasonic sounds. These are very low-frequency vibrations below the range of human hearing. Infrasound can travel long distances and even pass through the ground. Fossil evidence from skull cavities suggests adaptations for detecting such vibrations. Infrasonic hearing would have allowed dinosaurs to communicate across miles, warn of danger, or coordinate movement within herds. Modern elephants and whales use similar frequencies today. These deep sounds would have shaped dinosaur communication quietly and powerfully. From hearing hidden vibrations, we can explore how dinosaurs may have produced sound themselves. Certain dinosaurs had hollow crests connected to their nasal passages. These structures may have acted as resonating chambers, altering airflow to produce distinctive sounds. By changing head position or breathing patterns, dinosaurs could create calls with unique tones. Fossil reconstructions suggest these sounds were deep and far-carrying. Crests may have allowed individuals to identify one another or communicate across large distances without visual contact. Sound shaped identity as much as appearance. Crests were not just visual ornaments, but tools for communication. From sound production, we can consider how dinosaurs used vocalization socially. Communication was essential in large, open environments. Dinosaurs likely used a combination of sound, vibration, posture, and movement to send messages across space. Herds may have stayed connected through calls, while parents and young maintained contact through quieter signals. Long-distance communication reduced confusion and helped coordinate movement. It also warned of predators or guided migration. These invisible connections held groups together. Communication allowed dinosaurs to function as communities rather than isolated individuals. From communication, we move to specific examples preserved in anatomy. Parasaurolophus is famous for its long, curved crest. Inside this structure were winding air passages connected to the nasal cavity. Computer models suggest these passages produced deep, resonant calls similar to musical instruments. These sounds could travel great distances and may have been used for mating displays, warnings, or group coordination. The crest transformed breath into sound, turning the dinosaur into a living signal within its environment. These calls would have filled ancient landscapes with low, echoing tones. Sound added atmosphere to the dinosaur world. From vocalization, we can explore how sound moved through the environment itself. Low-frequency dinosaur calls likely moved not only through the air, but also through the ground as vibrations. Such signals could be felt as much as heard. Dinosaurs sensitive to these vibrations would have perceived messages even when visibility was poor. Ground-transmitted sound was reliable across forests and plains, unaffected by obstacles that blocked sight. This layered communication added depth to dinosaur interaction. their world was not silent. It pulsed with unseen signals. From sound perception, we turn to how dinosaurs may have used senses beyond hearing and sight. In dense forests or during low light, vibration detection may have been more reliable than sight. Large dinosaurs walking produced ground tremors that others could sense. Predators may have detected prey through movement, while herds stayed aware of each other's positions. Sensitivity to vibration offered constant environmental feedback. This awareness connected dinosaurs to the ground beneath them. It created a sense of presence even without direct contact. From sensing vibrations, we can explore how dinosaurs responded emotionally and behaviorally. Communication was not limited to noise alone. Dinosaurs likely combined vocal sounds with body posture, movement, and visual display. Raising crests, spreading feathers, or lowering heads could amplify messages. Sound and posture together conveyed intention without conflict. These signals reduced unnecessary fighting and clarified social roles. This combination of cues shows sophistication. Dinosaurs communicated with layered meaning. From this social complexity, we can step back and consider the overall sensory richness of their world. The age of dinosaurs was not a silent world. It was alive with calls, footsteps, wing beats, and low vibrations moving through air and earth. Communication flowed constantly, shaping behavior and survival. Dinosaurs lived within a sensory landscape far richer than fossils alone suggest. With senses and communication explored, we can now turn inward toward how dinosaurs grew, cared for their young, and lived together across generations. Many dinosaurs did not grow slowly over decades. Bone tissue shows that some species experienced rapid growth, especially during their early years. Large herbivores could gain dozens of pounds in a single day, transforming from fragile hatchlings into formidable juveniles within a few seasons. Growth rings in fossil bones, similar to those in trees, reveal periods of intense expansion followed by steadier phases. Rapid growth reduced vulnerability to predators and allowed dinosaurs to reach safer sizes quickly. This pace required abundant food and efficient metabolisms, suggesting highly active bodies rather than sluggish ones. Dinosaurs were built to grow fast when conditions allowed, compressing enormous physical change into surprisingly short spans of time. Fast growth reshaped survival. It turned weakness into strength quickly. From growth rates, we can begin to understand how dinosaurs protected their young during those vulnerable early stages of life. Growing quickly was a powerful defense. Young dinosaurs that increased in size rapidly spent less time in the most dangerous phase of life. Predators often targeted the smallest and weakest individuals. By growing fast, juveniles shortened that window of vulnerability. This strategy appears across many dinosaur groups, especially large herbivores. Rapid growth required constant feeding and stable environments, tying survival to ecosystem health. When resources were plentiful, growth offered safety. When conditions worsened, it became a risk. This balance between speed and stability shaped dinosaur life cycles. From protecting themselves through growth, dinosaurs also relied on reproduction strategies to ensure survival across generations. All known dinosaurs laid eggs. Fossilized eggshells show a range of sizes, shapes, and structures depending on species. Egg-laying allowed dinosaurs to produce multiple offspring at once, increasing the chance that some would survive. Nests were built in soil, sand, or vegetation, sometimes arranged in organized patterns. Eggs were vulnerable, but they allowed reproduction without carrying young internally. This strategy favored numbers over certainty. Egg-laying tied dinosaur survival to place and season. From eggs themselves, we can explore how dramatically their size could vary. Dinosaur eggs ranged from smaller than a marble to larger than a basketball. Small dinosaurs laid tiny eggs that hatched quickly, while giant sauropods produced surprisingly modest eggs compared to their adult size. Even the largest eggs were small relative to the adults they produced. This meant hatchlings began life extremely vulnerable. Egg size reflected trade-offs between protection, number, and parental investment. This contrast between egg and adult size highlights how growth filled the gap. From egg size, attention naturally turns to how many eggs dinosaurs produced. Certain dinosaurs laid large clutches containing dozens of eggs. Fossil nesting grounds show hundreds of eggs spread across wide areas, sometimes arranged in repeated layers. Producing many eggs increased the odds that at least a few hatchlings would survive predators and harsh conditions. This strategy relied on numbers rather than individual protection. Many young would not survive, but enough would to sustain populations. These vast nesting grounds suggest coordinated behavior. From laying eggs in quantity, dinosaurs also developed ways to protect them. Some fossil nests reveal adults positioned protectively over eggs, suggesting active care rather than abandonment. Certain dinosaurs appear to have guarded nests, maintained temperature, or defended eggs from predators. Nest structures show repeated use, indicating safe locations chosen carefully. Parental care increased survival odds, especially in species with fewer eggs. These protective behaviors narrow the gap between dinosaurs and modern birds. From guarding eggs, we move to how some dinosaurs incubated them. Several fossils preserve dinosaurs crouched over nests with limbs spread protectively, nearly identical to modern birds incubating eggs. This posture suggests brooding behavior using body heat to regulate egg temperature. Feathers may have enhanced insulation. Brooding required patience and energy, indicating strong investment in offspring. It also implies elevated metabolism capable of maintaining warmth. This tenderness challenges outdated views of dinosaurs as cold and indifferent. From brooding, we can look at what happened after eggs hatched. Fossil evidence suggests that some baby dinosaurs remained in nests for weeks or months after hatching. Their bones show growth stages incompatible with immediate independent movement. Parents may have brought food or defended the nest during this period. Staying put reduced exposure to predators while young grew stronger. Extended care deepened family bonds. From nesting behavior, we can examine how dinosaurs lived together beyond the nest. Trackways and fossil sites show dinosaurs moving in organized groups, often mixing adults and juveniles. Herd living offered protection, shared vigilance, and coordinated movement. Young dinosaurs benefited from staying near larger individuals. Social structures likely varied by species, but cooperation appears common. These group dynamics reveal community rather than isolation. From herd life, we can explore how dinosaurs coordinated movement and protection. In herds, adults often surrounded juveniles, placing the most vulnerable individuals at the center. This formation reduced predation risk and allowed collective defense. Herds could respond together to threats, confusing predators or standing ground when necessary. Protection was shared, not individual. With growth, care, and social life explored, we are now prepared to look outward again, toward how dinosaurs adapted to changing environments and evolving worlds. During their long history, dinosaurs experienced dramatic changes in Earth's climate. The planet moved through periods of intense heat, cooler intervals, rising seas and shifting rainfall patterns. Ice-free polar regions alternated with warmer global conditions, and carbon levels fluctuated. Dinosaurs did not merely survive these changes, they adapted to them. Fossil evidence shows shifts in body size, diet, and distribution corresponding to climate trends. Some species migrated as environments changed, while others evolved new traits to cope with heat, drought, or seasonal darkness. These adaptations unfolded slowly over thousands and millions of years, allowing populations to adjust without sudden collapse. Dinosaurs were not fragile specialists locked into narrow conditions. They were flexible organisms shaped by patience and time, able to persist as the planet itself transformed beneath their feet. This long-term resilience explains their extraordinary success. Dinosaurs were not static creatures frozen in one world. They were partners with a changing Earth, adjusting as climates rose and fell around them. Dinosaurs occupied nearly every terrestrial environment available. Fossils have been found in ancient deserts, dense forests, river floodplains, coastal wetlands, and open grassless plains. Some species were adapted to dry conditions, conserving water and feeding on sparse vegetation. Others lived in humid forests where food was abundant but competition was intense. Wetland environments supported large herbivores and predators alike, offering rich plant growth and access to water. This ecological breadth shows that dinosaurs were not limited to a single lifestyle. Their success came from specialization across environments rather than dominance of one. Different species evolved to fill different roles, creating stable ecosystems with layered interactions. This environmental flexibility allowed dinosaurs to spread widely and persist through change. With habitats ranging so broadly, it becomes possible to understand how some dinosaurs even survived in extreme regions. Fossils discovered in Alaska, Antarctica, and other high-latitude regions show that dinosaurs lived near the poles. These environments experienced long periods of darkness during winter and continuous daylight during summer. Polar dinosaurs had to endure cold temperatures and seasonal extremes. Some species lived there year-round rather than migrating away. Their presence suggests adaptations such as insulation, altered growth patterns, or social behaviors that improved survival. Forests once covered these polar regions, providing food despite the darkness. Dinosaurs were not confined to warmth. They extended their reach to the edges of Earth's habitable zones. Life at the poles required endurance rather than speed. These dinosaurs demonstrate how adaptable the group truly was, thriving even where sunlight disappeared for months at a time. In polar regions, dinosaurs faced extended winter nights lasting several months. Evidence suggests they adapted by slowing growth, altering activity patterns, or relying on stored energy. Warm-blooded or partially warm-blooded physiology would have helped maintain body temperature. Herd behavior may have provided warmth and protection during harsh seasons. Hatchlings likely emerged during summer months to maximize growth before winter. These adaptations allowed dinosaurs to endure conditions that would challenge many modern animals. Surviving darkness required more than strength. It required timing, cooperation, and internal regulation. From these extreme environments, we can now shift focus to the animals that lived alongside dinosaurs quietly and unnoticed. Dinosaurs did not rule alone. Early mammals shared their world for over 100 million years. These mammals were generally small, nocturnal, and cautious. Living in the shadows of giants, they survived by hiding, burrowing, and feeding on insects or plants. Fossils show mammals diversifying quietly while dinosaurs dominated daytime ecosystems. This coexistence shaped both groups. Dinosaurs influenced mammal behavior. While mammals filled ecological gaps, dinosaurs did not occupy. The balance was stable for millions of years. This shared world reminds us that dominance does not erase coexistence. Even during the dinosaur age, life diversified in parallel paths, waiting for future opportunities. For most of the dinosaur era, mammals stayed small, rarely growing larger than a house cat. Large body size would have put them in direct competition with dinosaurs, a losing strategy. Instead, mammals evolved traits like fur, keen hearing, and nocturnal habits. These adaptations allowed them to survive without confronting dinosaurs directly. Their small size reduced food needs and allowed rapid reproduction. Mammals endured not by challenging dinosaurs, but by avoiding them. This quiet persistence set the stage for later change. When dinosaurs disappeared, mammals were ready. But before that turning point, dinosaurs themselves were shaping the plant world in profound ways. During the mid-Cretaceous period, flowering plants began to spread across the world. Before this, landscapes were dominated by ferns, conifers, and cycads. Flowers introduced new colours, scents, fruits, and seeds. Dinosaurs walked through ecosystems in the midst of this botanical transformation. Herbivorous dinosaurs encountered new food sources, while insects and small animals responded to flowering plants as well. This shift reshaped food webs and landscapes permanently. The rise of flowering plants marked one of the most important ecological revolutions in Earth's history, and dinosaurs were active participants within it. This flowering world added complexity and richness to dinosaur ecosystems. From plants evolving alongside dinosaurs, we can explore how dinosaurs helped those plants spread. As dinosaurs fed on plants, they often swallowed seeds that passed through their digestive systems intact. These seeds were deposited far from the original plant, carried across landscapes by moving bodies. Fossilized dung containing seeds provides direct evidence of this process. Large herbivores acted as powerful agents of plant dispersal, shaping vegetation patterns over vast areas. This relationship benefited both dinosaurs and plants. Food sustained dinosaurs, and movement helped plants expand. This quiet cooperation shows that ecosystems are built on mutual influence. Dinosaurs were not just consumers, but participants in shaping the living world around them. Through feeding, movement, and sheer presence, dinosaurs shaped the structure of ancient ecosystems. Large herbivores altered plant growth, opened forests, and redistributed nutrients. Predators influenced prey behavior and population balance. Migrating herds reshaped soil and vegetation along their routes. These effects cascaded through food webs, influencing insects, plants, and smaller animals. Dinosaurs were not just inhabitants of ecosystems, they were engineers of them. This ecological influence explains why dinosaur extinction had such profound consequences. When they disappeared, the world did not simply lose animals. It lost entire systems of interaction. Measured by longevity, diversity, and global reach, dinosaurs were among the most successful animals in Earth's history. They thrived for over 160 million years, adapting to shifting climates, continents, and ecosystems. They evolved countless forms and behaviors, filling nearly every land-based role imaginable. Their success was not defined by strength alone, but by flexibility and resilience. Few groups of animals have ever matched their evolutionary achievements. With this long success established, we are prepared to face the final chapter. To understand not just how dinosaurs lived, but how their age came to an end and what endured beyond it. About 66 million years ago, a massive asteroid collided with Earth, marking one of the most dramatic turning points in the planet's history. This object, several miles wide, struck with unimaginable force, releasing energy far beyond any natural disaster humans have experienced. The impact occurred suddenly, but its consequences unfolded over years. It was not merely a collision, but a planetary transformation. Dinosaurs had survived volcanic eruptions, climate shifts, and continental movement. But this event was different in scale and speed. The asteroid struck at a moment when ecosystems were stable yet vulnerable. In an instant, the long age of dinosaurs entered its final phase, not through gradual decline, but through abrupt catastrophe that reshaped life on Earth forever. This impact did not act alone. It triggered a chain of events that followed one after another. To understand the extinction, we must look at where the asteroid struck and what that location unleashed. The asteroid struck near present-day Mexico, forming the Chicxulub crater beneath the Yucatan Peninsula. This region was rich in limestone and sulfur-bearing rocks. When the asteroid hit, these materials were vaporized and blasted into the atmosphere. The location amplified the devastation. The impact excavated a crater more than 100 miles wide and sent shockwaves through Earth's crust. Geological evidence around the world confirms this site as the impact zone. The position of the strike mattered as much as the strike itself, turning a collision into a global event rather than a regional disaster. From this single location, destruction spread outward across the planet. The place of impact determined how the atmosphere, oceans, and climate would respond in the years that followed. The energy released by the asteroid impact defies ordinary comparison. Scientists estimate it exceeded the combined power of billions of atomic bombs detonated at once. Rock instantly vaporized. Shock waves raced through the planet. The atmosphere ignited with heat. Earth itself responded like a struck bell, trembling from pole to pole. This energy was not localized. It propagated through air, land, and sea, setting off earthquakes, landslides, and volcanic responses. No ecosystem remained untouched. The force alone would have killed many organisms immediately, but it was only the beginning of the devastation. Energy reshaped the planet in seconds, but its aftereffects lingered. From raw force came fire, water, and darkness, each contributing to the collapse that followed. As debris from the impact was launched into the atmosphere, it eventually fell back to Earth as molten fragments. These red-hot materials ignited forests and grasslands across continents. Evidence of widespread wildfires appears in the fossil record as soot layers found worldwide. Flames spread rapidly, consuming vegetation and releasing massive amounts of smoke into the air. Even regions far from the impact zone burned. Firestorms eliminated plant cover, destroyed habitats, and removed the foundation of many food chains. Fire turned Earth's surface hostile. What survived the initial blast now faced an environment stripped of shelter and sustenance, pushing ecosystems closer to collapse. The asteroid struck partially in shallow ocean, displacing enormous volumes of water. This generated tsunamis hundreds of feet high that raced outward at incredible speeds. Coastal ecosystems were obliterated as waves surged inland, carrying debris and sediment far from shore. Geological layers show signs of these floods in places thousands of miles away. Oceans, usually sources of stability, became agents of destruction. Water completed what fire began. Land and sea alike were destabilized, leaving few refugees untouched by the unfolding disaster. Perhaps the most devastating effect came after the initial chaos. Dust, ash, and sulfur aerosols filled the atmosphere, blocking sunlight. Daylight dimmed to twilight, then darkness. Photosynthesis slowed and then largely stopped. Temperatures dropped sharply. This impact winter may have lasted years. Plants withered, and ecosystems dependent on sunlight began to fail. Without light, life faltered. The planet entered a long, cold pause where growth became impossible and survival depended on stored energy alone. As plants died, herbivores starved. As herbivores vanished, predators soon followed. Food chains unraveled from the bottom upward. Fossil records show sudden declines in species across land and sea. The extinction was not selective or gradual, it was systemic. Organisms that depended on stable, productive environments could not endure the prolonged darkness and cold. This collapse marked the true end of the dinosaur-dominated world. It was not the asteroid alone, but starvation and ecological failure that sealed their fate. The extinction event eliminated more than 75% of Earth's species. Dinosaurs were among the most visible losses, but countless plants, marine reptiles, insects, and microorganisms also disappeared. Entire branches of life ended. The planet's biological diversity was reset. Recovery would take millions of years. This was one of the most severe mass extinctions in Earth's history. Yet even in this devastation, some life endured. Survival depended on small size, flexibility, and the ability to endure scarcity. Not all dinosaurs vanished. A small group of feathered theropods survived and became modern birds. Their size, diets, and mobility gave them an advantage. Some could fly, others could eat seeds or insects. They required fewer resources and could shelter more easily. These traits allowed them to endure when larger dinosaurs could not. Birds carry the lineage of dinosaurs forward into the present. This survival reframes extinction. Dinosaurs did not disappear completely. They transformed, adapting to a changed world rather than yielding to it. Every bird alive today is a living dinosaur. From sparrows and pigeons to eagles and penguins, they are direct descendants of the ancient theropods that once walked among giants. Their bones, feathers, lungs, and behaviors all trace back to deep time. When a bird takes flight, it carries with it the legacy of the dinosaur age. The world of dinosaurs did not end, it changed shape. With this realization, the story comes full circle. The age of dinosaurs is not over. It surrounds us quietly, on wings, in song, and in the living present that grew from a world long past.